So the next type of automata that we will learn of is called the non-deterministic finite automata. Remember that a non-deterministic finite automata is also a finite automata, except that it is non-deterministic, unlike the deterministic that we have seen. The fundamental difference between a DFA and an NFA is this, right? Suppose if you are at any state, let's call this state as Qi, right? So on any given input, let's say my alphabet consists of two symbols, A, B, right? Suppose on a symbol A, on QA, in a deterministic finite automata, I might go to QJ, right? In a deterministic finite automata. In a non-deterministic, so in a deterministic finite automata, this will happen, right? Of course, I also have to define the transition on B. I have to define transition both on A and B. In a non-deterministic finite automata, what happens here is, if I am at a state Qi, on transition A, look at this, on transition A, again, on transition B also, I need to define a transition to some other state, okay? Now here on transition A, right, I can go to multiple states. For example, on transition A, I can go to Qj and also Qk, which means if you are at a given state and if you get an input symbol, right, you can transition to multiple states, or in this case, there is no transition to B, or you can choose not to have any transition itself. Both of those are valid in non-deterministic finite automata. And the word non-deterministic comes into play here because in a deterministic automata, you know exactly, or you can determine exactly where you will go given, if you are at a given state, when you input a given symbol. In the case of a non-deterministic finite automata, for example, if I'm at this state Qi, if my input is A, I could be in Qj or I could be in Qk. So you cannot point to a single state and say, if you're in this state, if you get an input symbol A, you will be in Qj. You cannot fix one state and say, you will be in this state. You could be in Qj or you could be in Qk. Okay, that's a fundamental difference between a DFA and an NFA. And for an NFA, for example, take this case, right? On input symbol B, right? On symbol B, there is no transition at all. And that's perfectly valid in an NFA, right? So if you think about it, how do we mathematically define the same thing? Okay, I hope intuitively understood this. Again, don't worry about it. We'll look at many examples in this video through which you'll understand this concept completely. Now, but let's define the mathematical aspects of a non-deterministic finite automata, because we want to be as rigorous as possible. Now, an NFA is also a 5-tuple. An NFA is also a 5-tuple, right? It has, so an NFA, okay, it's a 5-tuple, right? So you have a machine M, you have the set of states, the symbols, or the set of symbols, which is called the alphabet, the transition function, the initial state, and the set of final states. Okay, this concept stays the same. This is the set of states. This is the set of all the input symbols that it would take. This is your alphabet, stays the same. Your initial state, you need to have a distinct initial state. You could have a set of final states which is empty. The fundamental difference comes when you define your transition function in an NFA. Your transition function in an NFA is defined as follows. You're at a given state, right? Given a state and an input symbol. Given a state and an input symbol from the alphabet, what it would return is 2 power q. I'll explain what 2 power q here is. Before we go into what 2 power q is, in a DFA, how would the transition function look like? The transition function looks like this. You take an input, which is the state, and the symbol, the input symbol from the alphabet, and you return another state. In your DFA, this is how your transition function looks like. In your NFA, this part stays the same. You take a state as an input, you take an input symbol as the second input. Your output now, this is called the power set. This is called the power set of Q. Okay, what is power set? Power set is the set of all subsets. It is a set of all subsets of Q. For example, just for simplicity, right? Let's say my set of states is Q0, Q1. Let's just say, right? Then 2 power Q is, it is a set of all the subsets. What are all the subsets? An empty set is a subset of Q. Yes. A set which consists only of Q0 is a subset of Q? Yes. A set which consists only of Q1 is a subset of capital Q? Yes. A set which consists both Q0 and Q1. This is also a subset of Q, right? So this is called the power set, and it is written as 2 power Q because if you have n elements here in a set, if you have n distinct elements in the set, then the number of elements in the power set, so the number of elements in the power set is equal to 2 power n. That's why they often use this notation, which is 2 power Q, called the power set, which means, now let's understand what this means intuitively. So your transition function basically says, given an input, given an input state that you're currently at and a symbol, right? At a state, if you take a symbol, your output could be an empty set. Like look at this here on transition B, nothing is defined, right? And that's valid because this function takes these two inputs and its output can be an empty set, which means on some inputs, I don't have to define what the output state is because my output state itself is empty, right? In this case, look at this. Qi, see delta on Qi comma B is a null set here in this case because Qi on B, I have not defined where it goes to, right? So in this case, this is true. Similarly, in this case, on Qi comma A, right, I can go to any of these states, Qj or Qk, right? So what is this? This is a subset of the set of all the states that you have, right? So your transition function takes the current state and an input symbol and it returns a subset of, and it returns a set of states. That set could be empty set also. Okay, that's how you define your non-deterministic finite automata mathematically. Now you might wonder, why should we care about defining something called as a non-deterministic finite automata? Why can't I just stay with DFA itself? Is there some advantage of constructing and introducing this concept of NFA in the real world? There are actually. I'll show you lots of examples through which we can easily observe that constructing NFA is significantly easier in the real world than constructing DFA. Okay, actually we'll solve all the problems that we have seen, that we have solved extensively when we learned about DFA. We'll also solve them using NFA as part of this video and the next few videos, right? So let's go through this. So this is the mathematical definition and this is the most important differentiating factor between a DFA and an NFA. In a DFA, you have to get a single state as output. Here the output could be a set of states and that set could be an empty set also. Okay, so with that introduction, let's look at some examples. Again, it's best to understand this concept with examples. Look at this. My Q0 is my initial state. Look at this. My set of states is Q0, Q1. Right? Q0, Q1. Now, what is 2 power Q now? 2 power Q is the empty set. We have just seen this, right? Set Q0, set Q1, and set Q0, Q1. Right? There are four elements as part of the power set. Each element is also a set in itself, right? Now, my alphabet itself consists of two symbols A and B. Now, let's take this NFA. This is an NFA because if I'm at Q0, look at this. If I'm at Q0, if my input symbol is A, look at this. Q0 input symbol is A. I can stay in Q0 itself. I can stay in Q0, right? That's it. I can stay in Q0. So this part is done. Good. Now, what about Q0 on B? Look at this, Q0 on B. I can stay in Q0 or I can also go to B. I can also use this. Look at this. If I use this link or if I use this edge, right? From Q0, I stay in Q0 or I can go to Q1 also, right? So very simple. Similarly, delta on Q1 comma A. I'm in Q1. If I get an input A, where do I go? I go to Q1. Very good. So now delta, this function delta, right? The transition function, Q1 on B, what happens? Q1 on B, it's not defined at all. So this is a null set, right? If I get this, I just terminate, right? Very simple example. Look at this. Here, if you notice, this is a set of two states. This is an empty set, right? Here you have just a set of one state, This is a fundamental difference between an NFA and a DFA. Now comes the very interesting question, which is how do NFAs accept now? See, this is an example of an NFA, right? Now here is an example of an NFA. Now, how do we determine which words are accepted by an NFA? That's a very important question, because there are multiple states I could transition to. So, okay, let's go step by step and understand this. So let's take this diagram. Okay. So we'll understand how acceptance by an NFA works quickly. So for example, if you take this example, right? What happens if I have word AB? My word consists of two symbols or a sequence of two symbols AB. So I start here on A itself. Look at this. On A, I can stay in Q0. So what is one possibility? I start at Q0. On A, I stay at Q0, right? On B also, I can continue to stay at Q0. So this is called a transition path. This is one transition path, which means I start at Q0. On A, I stay here. On B, I stay here. This is one transition path. There is another transition path, which is I start at Q0. On A, I can jump here. On A, I can jump here, right? I can move to state Q1, because Q0, when the input symbol is A, I can either go to Q0 or I can go to Q1 also. There are two possibilities here, right? So the second transition path here is Q0 on A goes to Q1. Now Q1 on B, look at this, Q1 on B goes to Q2. And if you notice, Q2 is a final state. If any of these transition paths, if any transition path leads to a final state, leads to a final state, we accept the word. If this happens, we accept the word, right? So in this case, AB is accepted by this machine, because there is at least one path. There is at least one path wherein we start with Q0 and we input each of these symbols one after the other, and we can reach the final state. Of course, this doesn't reach the final state, but this reaches the final state. Even if one such path exists, if any transition path, again, these are called as transition paths. And this concept comes from graphs, right? In graph theory, a set of vertices that are connected by edges is called as a path, right? So this is like a path. Q0 to Q1 to Q2 is a path. Q0 to Q0 to Q0 is also a path, because it's a set of, or you can think of it as a sequence instead of a set. A sequence is a better way of actually discussing this. It's a sequence of vertices such that you have edges on these input symbols. Okay. So now let's assume I have an input AA. Would AA be accepted? Let's see. So I start from Q0. On input A, I can go to Q0 or I can go to Q1. There are two possibilities, right? So let's draw two transition graphs. Now again, I get A here. So if I get A here, I stay in Q0. Now on Q1, A is not at all defined. Which means I just terminate this and I say don't accept. Because A, look at this. Q1 on A, let's actually write this down. Q1 on A takes me to a null state. Okay, there is no state. There is literally no set of states that I can go to, because the transition itself is not defined, right? Which means I'm lost here. I cannot go to Q0. I cannot go to Q1. I cannot go to Q2. Remember, I can't stay in the same state also. That is also not valid. Because the output is not yet defined, we will terminate this path and we'll say, just terminate this path and say, sorry, we'll not accept this. Okay, very simple. Okay, good. So in this case, what's happening? I'm starting at Q0, continuing at Q0, staying at Q0. But Q0 is not a final state. So I will not accept AA. So to decide whether a string or a word is accepted or not, we have to try out all the possible transition paths. All possible transition paths, because the definition says if any transition path leads to a final state, we accept the word, which means we have to try all the transition paths. from a computational viewpoint, you can think of this as one process or one thread. See, if you have to implement this in a computer software, if you have to implement this NFA in a computer software, what would you do? You would start at Q0 on input A. See, there are two paths possible now. On input A, you can either stay in Q0 or you can stay in Q1. So you can think of this as parallel programming. This is one thread or one process. This is another thread or another process. Again, if you don't know what threads and processes are, don't worry about that. We'll learn it in operating systems. Okay. But if you know what they are, you can think of this as one computational thread or one computational sequence of operations, and this as another sequence of operations, right? So NFAs are also interpreted as a parallel processing system. Okay, you can think of NFA as parallel processing system because this type of thing will never happen in a DFA, right? So this is one computational interpretation of NFA. Again, you don't have to build a multi-threaded system when you're implementing an NFA. You can also implement NFAs with data structures like sets if you were to implement this in software code. Okay, sounds good. Now let's again, with all this, we understood what is the acceptance by an NFA, all of these things. Now let's actually solve a bunch of problems. If you recall, we solved a bunch of problems when we learned DFA. I made a claim here that NFAs are easier to construct than DFAs. Let me actually show you with a bunch of examples that NFAs are actually much easier to construct than DFAs. Okay, so we'll walk through many examples that we have gone through when we constructed DFAs, but since it was the first time when we constructed DFAs, we went much slower. Now we'll go slightly fast because it's very simple actually to construct NFAs. Okay, let's assume for all of this discussion, I'll assume that my alphabet consists of two symbols A and B. Now I want to construct an NFA. Again, this whole discussion is only about NFAs. I want to construct NFA which accepts strings that start with a A. Okay, let's see how to do that. Okay, so this is my initial state Q0. Okay, if I get if it starts with A, I want to go to a final state. Look at this. If it starts with A, I want to go to a final state. Now, once I'm in this final state, look at this. Once I'm in this final state, whether I get A or B, I don't care because I've started with A. Now, this is an NFA. This is not a DFA. This is not a DFA. Why is it not a DFA? Because my input alphabet consists of two symbols, A and B. Transition only on A is defined here. What about transition on B? It's not defined anywhere. Transition on B is not defined. This is not DFA because Q0 on B. Look at this, Q0 on B. This is not a DFA because Q0 on B is a null set. It's not defined. Right? So now, in the case of, again, remember, in the case of, if you were to design a DFA, what would we do? We would actually create a dead state. Imagine if I were to create a DFA corresponding to this. How would I have designed the DFA? Q0 on input A, I would go to a terminal state or I would go to a final state. On input B, okay, I would go to a dead state. This is my Q2, I would get stuck here. All right, this is my, if you notice, this is an NFA. This is an NFA and this is a DFA. Right? Here I had to create a dead state to account, because for every vertex or for every state, I had to define all the transitions on all the input symbols in the case of a DFA. So I needed the concept of a dead state, right? When I was designing DFA. In this case, I don't need that concept because if my first input symbol, let's assume I'm at Q0, if my input symbol is B, okay, this will say I don't know where to go to. I'll simply terminate this and not accept. That's it, done. So you don't require the concept. You don't need the concept of a dead state in the case of an NFA, right? So this is how NFAs and DFA, again, designing NFA was much simpler here because I didn't have to worry about this whole dead state case, right? So I hope you got the fundamental difference between an NFA and a DFA. One of the differences here, again, this is only one type of difference because you don't have multiple transitions here, right? For example, on Q0 on A, you exactly go to one state. There is no case where you go to multiple states like this. There is no this type of condition here. We'll see that in some of the examples that we'll learn later. But we don't need the concept of a dead state itself. Okay, so this is one example. Let's go to the next example. Imagine if I want to, again, let's figure out a bunch of examples for starting with. Okay, this was starting with A. So that's why I've grouped all of them into a single problem. This is 2A, 2B, 2C. Starts with AB, starts with ABA. Now let's see. If it has to start with AB, again, designing is super easy enough, right? On A, I will go to Q1. Then on B, I'll go to Q2. Now the moment I reach here, I know I have started with A and B. Now whatever I get, I'll continue to be here. That's it. It's that simple. Look at this. Because I don't have to worry about a dead state, creating, see, all the dead state business is gone now. Okay, when we have to design automata like this. Literally, you can draw this in like 20 seconds. Now let's look at the similar example here, right? So if I want this to start with ABA, look at this. Again, this is very simple. Start with ABA. Starts with A, then B, then A, right? I reach a final state now, Q3. Now, whatever input I get afterwards, I'll stay in the same state. Because with ABA, I'm guaranteed to go here, right? That's it. Very simple. If I get any other input, any other prefix here, any other prefix, anyway, the output state will be null because I've not defined those transitions. The output state is a null set, which means the automata will say, sorry, I don't know what to do, and it will terminate. It will not accept that string. Very simple case. Okay. Now let's look at, okay, what if it has to start with AABB? This is also simple, right? Q0, A, my first A, Q1, again an A, Q2, B, Q3, B, that's it, AABB, Q4, anything else, I'll continue to stay here. See how simple this has become. No headache of dead states here, right? Very, very elegant solution, right? Of course, there are some, because I don't have them, I also have to, if I have to implement this in software, I have to handle the case that at a state, a transition is not defined. So I'll simply terminate that process or terminate that program and say, and it will return that this string is not accepted. Very simple case here. Again, now we have seen starting with, right? Now let's see cases of ending with. Okay, if you want to accept strings, again, same situation, right? My alphabet is the set of AB. Everything stays the same. I want to accept strings that end with A. How do I do this now? We have seen the starting, right? We have seen the startings now. Let's see the endings. Few examples, simple examples. Okay, so here what I'll do here is, look at this. I'm at Q0, right? It has to end. Look at this. It has to end in A. So what I'll do here is, if my input is, okay, let me just draw this quickly. Okay, then you will be able to understand this. Okay, that's it. Look at this. Now let's take some examples and understand this. Here you have on Q0, on input A, you can stay in Q0 or you can go to Q1. Suppose if my input is A itself, my W1 is just a single symbol A. What happens now? There are two paths. One path is Q0 on A stays in Q0. The other path is Q0 on A goes to Q1, which is a final state, right? Which is a final state, which means single A is going to be accepted by this, right? Similarly, what if I have BA? BA, I can stay in Q0. That's one thread of computation. Okay, that's one path. Okay, instead of thinking about threads of computation, let's think about it as transition paths. Much more easy. So my input is, let's say, BA. Okay, it ends with A. It should be accepted. Okay, this model should accept it. Let's look at one transition path. I stay in Q0. On B, I stay here. On A, I stay here. Not a final state. But there is another transition path. Q0. On B, I stay here. On A, I go here. So there is one transition path, which is this followed by this, which takes me to a final state. Hence, this is accepted. Look at how easy it is for me, because this is allowing me to have two transitions, right? Two possible transitions on a given state on the same input symbol. On the same input symbol, same state, it is now letting me have these two cases, and hence construction has become much simpler. Let's say I want to have ending with BA. Again, this is super simple. We can just literally draw it in no time. Okay, ending with BA, right? Ending with BA. BA, right? BA, Q2, that's it. Now, if my input itself is BA, what happens now? I can get stuck at state Q0. I think I've done it good. I've done this correctly, right? So I can get stuck here, or I can take this path. Yes, very good. If my word is, let's say, AABA, right? AA, there is only one path. Here on B, I have two possibilities. So A, I'll stay here. On B, I can again get stuck here, or I can take this alternative path and I'll reach a final state. So it will be accepted. Look at how simple it has become. Because again, all this is because this is allowing me to have this. And I don't need this case of dead states. No headaches of dead states. See how much simpler it has become to design these automata, right? If especially NFS. The same thing if we were to do DFS. You can go back to some of our previous videos where we spent a lot of time designing these the equivalent deterministic finite automatas. Again, for every NFA, you can construct an equivalent DFA. We will learn of that in the next few videos. Okay, we'll see, given an NFA, how to construct the equivalent DFA for that. That's very possible, by the way. Okay, so for every NFA, you can construct a DFA, and actually, technically speaking, every DFA is also an NFA. DFA is an NFA, right? Because if you look at it from a pure mathematical viewpoint, Q is also a subset of 2 power Q. Q is a subset of 2 power Q, right? So if you think about it, because if you look at the core mathematical formulation itself, right? An NFA is allowing you to have any set here, right? Any set will also consist of singleton sets, no? Right? If you think about it, it will have singleton sets also, which means a DFA, so that way DFA is a special case of an NFA. NFA is a generalization, but we'll also see in the future videos that for every NFA, there is an equivalent DFA, and we'll see how to construct that. Just wanted to bring that to your notice now. Okay, so one more case, one more ending with situation, right? Ending with ABB. Again, this is trivial. So I'm at state Q0, whatever it is, I don't care. Then on A, I go to Q1, on B, I go to Q2, on B again, I go to Q3. That's it. I'm done. This is how simply we can design NFS. Okay, so enough of praising NFS. Of course, NFS have their own disadvantages, that implementing them in software is much more tricky. Designing them is much more easy. Okay, so now let's say 4A. Okay, so now let's go into the case of substrings. We have seen these examples also, right? In the case of when we learn DFS. Now, if I want to accept strings, again, the example is my alphabet here is set AB. I want to accept all strings that contain BA as a substring. How do we design that now? BA as a substring, right? Again, this should be easy. Let me just draw this. Okay. So this is my initial state. On any transition, I'll have this. On BA, I'll create this. That's it. This is my end state. Now, once I reach an end state, because I want substring, right? Whatever is the input, I don't care. Look at this. Initially, whether the input is B or A, I'll stay here. Right? For example, imagine if my string is BA itself. One path will get stuck here. The other path will jump to this. Very, very simple design. Look at this. There's just a path. See, literally, how did we design this? A loop, self loop here with A and B. BA, because it's a substring. After BA, I can have anything. That's why I created this. Similarly, substring ABA. Again, super trivial to create this. Okay. Q0, because I want substring. Substrings can start with anything else, right? A, Q1, B, Q2, again A, Q3, right? Again, since it's a substring, it could also end in anything. That's it. ABA. Literally in 30 seconds, you can design these automata. If it's an NFA, right? You don't have to think too much about dead state. All the boundary cases, you don't have to worry about them. Okay. Now let's go to 4C. Okay. The problem 4C is substring ABAB. Again, this is super simple. Again, I'm showing you so many examples so that this becomes, you'll also feel that this is actually trivial and super easy to construct. More examples, more the confidence that you would get, right? AB, A, B, yes. So this is my final state, Q4. Again, since it's a substring, that's it. The structure is so easy to absorb, right? Super easy concept. Now let's go to a slightly different problem. Suppose if I want my automata, my NFA, to accept strings that start and end with A. We have seen DFAs for these examples also, right? So let's see, starting and ending with A. Now, how does that work? This case is slightly tricky. Look at this, starting with A. Okay, starting with A, I should accept it. Okay, starting with A, I should accept it. But ending also should be with A. Starting and ending with A. So starts in A, and let's say ends also in A. Okay, so I'll accept this. Now on AB transitions, I will have this. Now if a string starts with A, ends with A, I'll accept this. This part is cool. Okay, this part. See, for example, does this accept ABA? Yes. Does this accept AAAA? Yes. A. Right? One of the paths. Look at this. One of the paths takes me to the final state. If I use the other path, AA, then third A, I don't have the transition here. I'm lost. Right? But I have this A, two A's, and then the fourth. So 1A, 2 A's, and the final A. Yes, this also accepts this. There is one case that this machine does not accept. Single A. Look at this. Single A starts with an A and ends with an A. But with single A, I just go here, which is not a final state. Right? So I also need to add this edge here. So one more edge is needed here. The moment I add this edge with A transition, single A is also accepted. So lot of people make this mistake of not adding this A. This A is the critical part here. If this A is there, it will also accept a single character word, right? Or a single symbol word A, which starts and ends in A. Right? Very simple case here. So this edge is the important case. Otherwise, everything else is cool. Again, simple. This is certainly much simpler than a DFA. But this is an important case that you should not miss out. Okay. Starts and ends with the same symbol. Let's see. So which, again, what all symbols do I have? I have AB as symbols. Right? These are my input symbols. Right? So starts and ends with the same symbol. How do we design this? Again, this should be simple. So let's assume starts with A. Let's take that case, right? Starts with A and ends in A, right? So this is one case. So this is my AB case. This is my Q2, which is a final state. I'll also have this. Okay. So this starts in A, ends in A is taken care of. Now, similarly, I have to do starts in B, ends in B, right? So, sorry, starts in B and ends in B. Starts in B, ends in B. Yes. But if I just get single B, right? So that also I need to take care of. So single A or single B, I directly jump to the final state. Look at this, single A, single B, I jump to the final state, right? And now if you look at it logically, this path facilitates single A, single B, this path, right? On the other hand, these paths, this path enables A, something followed, starting with A, ending with A, something in between. This path, okay, oh, I need to add this also, I'm sorry. AB also has to be there. I forgot. Okay. Now, starting with B, something in between and ending in B. Yes. So, starting and ending with the same symbol. This is your NFA. That's it. Very simple case here. Very, very simple case. Okay. Now, let's look at slightly more complicated cases. Starts and ends in different symbols. Shouldn't be rocket science, right? Starts and ends in different symbols. Let's actually draw this. Q0. So, let's say starting with A, I go to Q1 and ending in B. That's what the two different symbols are, right? So Q2. This is one possibility. Now in between, if I get A's or B's, I will continue to stay here. Very easy. Now the other possibility here is starting with B, right? Starting with the B and ending in A. Okay. In between whatever symbols I get, I will take care of this. Now here we don't have to take care. Again, here we don't need this type of edge or this type of edge here, because single A should not be accepted by this machine. Single B should not be accepted by this machine because they end and start in the same symbol, right? So you have AB path here, you have BA path. For everything in between, you have this. See how easy it is to design these NFS. I mean, at the cost of repeating myself, I still feel that this is like super easy to design. That's why in real world, when you have complex systems, right? When you have complex systems, when you have fairly complex systems, people tend to design NFAs because designing the NFA itself is easy, right? Once you design the NFA, computational implementation, software implementation of it, there are multiple ways of doing it, either using concepts like multi-threading or special data structures like sets, etc. Okay, I'll not be able to go into them right now because for that you can use some of our notes and videos in data structures and algorithms on how to implement data structures like sets, or you can also wait for you can also check out our operating systems content. We'll discuss this in operating systems also, on how to build multi-threaded code and all of that, right? So again, you might have learned multi-threaded code in your at your undergraduate level, C programming or Java programming, etc. Okay, so the software implementation is slightly trickier, but designing the NFA itself is very easy if you have a complex system. If you have a simple system, imagine if I had, instead of a complex system, if I had a simpler system, then people tend to design DFAs because software implementation is straightforward. Software implementation of DFA is straightforward, right? Again, nowadays, the software implementations are not that hard, to be honest with you, because there are lots of special purpose tools, right? Wherein you can just define what you want, or you can define the set of strings that your automata should accept, and it's very easy to design them. They're almost like semi-automated systems to do this for us now. We'll learn that when we learn compiler design. Okay, so there are tools like Lex, etc. that we learn when we learn compiler design, where if you just define the language that your automata should accept, it will literally generate the automata for you, right? So it's become that simple, that much automated now. Okay, so back to our discussion here. So starts with AA or BB. Let's look at this. Starts with AA or BB, right? So again, very simple. So starts with AA, right? So A, Q1, B, Q2. So this is starts with AA. So this is starts with AA. Good, right? So after AA, whatever I get, I'll continue to stay here. But I could also have B also. B and then B. So this says starts with AA, starts with BB, right? Starts with AA, starts with BB. Anything that I missed? Do I need this? No, I don't need this. I don't need this. A, B, both are taken care of. Yes, that's it. Starts with AA and BB. That's it. This is my automata now. Very simple. See how easy it is to construct. Let's look at one more example. Starts with AA or BB. Sorry, ends with. Sorry, not starts with. Sorry. We saw the starts with here, right? Ends with AA or BB. Again, this should be simple. So given Q0, if I keep getting some symbols, I'll stay here. But then if I get A, right? If I get AA, I'll reach the final state, which is Q2 now. Okay, no more transitions here because it's ending with, right? Similarly, ending with BB. That's it. So if I keep getting inputs, I can stay here. That's one possibility. Ending with AA, ending with BB. That's it, done. It's that simple a machine here. This is my final state. Yes, makes sense. Now let's look at slightly more complicated examples, right? Suppose if you want the fourth symbol from the left to be B. Suppose imagine I have a word. Let's assume X, Y, Z are symbols. Okay. These symbols can be A or B, right? So these are variable names for symbols. Okay. Okay. X, Y, Z can be A or B. Okay. Then I have a B. Then I could have a word. So U here is some word. U here is a word. Okay. Now here if you notice from the left, my first symbol, second symbol, third symbol, fourth symbol is B. From the left, I want the fourth symbol to be B. To give you some example, let's assume I have A, B. From the left, the fourth symbol is B. So it should accept this. Similarly, if I have, let's say A, B, A, B, A, B, B. From the left, the fourth symbol is B. So it should accept this. For example, the third example, right? Suppose if I have A, B, B. From the left, the fourth symbol is A. So it should not accept this. How do you design an NFA for this? It's actually much easier to design an NFA for this than a DFA. It's very simple. Okay. So let me show you. So my first symbol, A or B, I don't care. My second symbol, A or B, I don't care. Right? My third symbol, A or B, I don't care. My fourth symbol has to be B. First symbol, second symbol, third symbol. My fourth symbol has to be B. If my fourth symbol is B, I reach a final stage. Once I reach a final stage, I don't care what my fifth, sixth, seventh, eighth symbols are. That's it. That's all there is. It's such a simple thing to actually design. The DFA is slightly more complex, not too complex, but NFA is super easy to construct. Let's take one more example, similar example. The fifth symbol from the right, here it was from the left, right? The fifth symbol from the right is A. Look at this, fifth symbol from the right. A, 1, 2, 3, 4. I can have any symbol here. Here I can have any word. Here I can have any word, but from the left, from the right, right? 1, 2, 3, 4. This is the fifth one. Fifth one has to be A. How do we design an NFA for this? Again, very simple. At the very beginning, right? This can be any word, right? So if I get an input A or B, I'll continue to stay here, right? Then if I get A, I'll go to my Q1 state here. Look at this. I'll go to Q1 state. So this corresponds to my Q0. Seeing this A goes to Q1. Now after seeing A, I have to see 4 more characters or 4 more symbols, right? So on AB, I go to Q1. Again on AB, I go to Q2. So A, I have seen it. 1 symbol, 2 symbols, 3 symbols, and 4 symbols after A, right? So, okay, that's it. Q4. That's it, right? So let me just think about it. So I have seen any number of symbols at the beginning, doesn't matter. I see an A. After seeing an A, I have to see exactly 4 symbols. 1, 2, 3, 4. Yes, I reach a final stage. Here there is nothing else because this is ending in, right? When talking about this right side, this is the ending part. So no more loops like this. That's it. So simple. Let's look at some more examples. So now let's design an NFA which accepts strings that contain exactly 2 A's. Remember that these 2 A's need not be consecutive, right? So let's actually design this. So I start at Q0. So here I know that I have seen 0 A's. So I'll keep track of these states like this. Okay, I'll keep track of these states, right? So I'll make this as my final state. Here I've seen 0 A's, 1 A, 2 A's. So I'll have these A transitions here. If I keep seeing B's in between, I don't care how many B's I see in between, right? I don't care how many B's I see in between. I only care about exactly seeing 2 A's. If I see anything more than 2 A's, the transition is not defined here, right? So I don't care how many B's I start with. The moment I see an A, I jump here. I don't care how many B's I see again. The moment I see another A, I jump here. Now I can't get any more A, right? That's how you design a very simple NFA which accepts strings that contain exactly 2 A's. What about at most 2 A's? Very simple. You just change this diagram slightly. Because this is 0 A's. The diagram more or less stays the same. Let me show you this. Okay. There is a very subtle difference here. A, transition on B, A, transition on transition. So this is Q2. I don't care about B's, right? So here if you notice, this is accepting state because this will accept 0 A's, this will accept 1 A, this will accept 2 A's. So when it says at most 2 A's, I could have 0 A's, 1 A or 2 A's. I don't care about B's. I really don't care about B's, right? So even if I have 0 A's, for example, if my input symbol, this is an interesting boundary case, right? If my input symbol is B, it accepts this because my initial state is the final state, right? It accepts this. The reason being it has 0 A's because we are saying at most 2 A's. This automata will also accept empty string because this has 0 A's. Very simple modification of the above one. Again, we saw this type of transformation, this type of subtle change even when we learned DFS. Now, what if I have a slightly more different example? What if I have at least 2 A's? Okay, look at this. Here I have at most 2 A's. Here I have exactly 2 A's. Now I want at most 2 A's. Again, a small change. Okay, look at this. Here I'm counting 0 A's, right? If I get an A, I go to this state, right? If I keep getting B's, I don't care. The moment I see 2 A's, I go to my state Q2. If I keep seeing A's and B's, because it says at least 2 A's, if I see 3 A's also, I should accept this. The only change here is, if you notice from the previous diagram, the only change here, there is only transition on B here. There is a transition on A also. So now if I see a string like this, A, it will accept this. A. I don't care about B's. So at least 2 A's. I need at least 2 A's. Once I reach this state, if I get more A's or B's, I'll keep accepting it, right? Another example. Suppose if number of A's is 2 mod 3. We have seen the modulo operator, right? When we learned about DFS. So let's design with 3 states. Q0 is my initial state. This corresponds to remainder of 0. This corresponds to remainder of 1. This corresponds to remainder of 2, right? And this will be my final state. How do my transitions work now? I don't care about B's, right? I really don't care about B's. So B's, let's just keep them here as is. Once I have zero A's, I stay here. Once I get an A, I go here. Once I get 2 A's, I go here. Once I get 3 A's, the remainder becomes 0, right? So I go here. Right? That's it. That's all is my NFA. Now, one thing, if you notice, this is both an NFA and a DFA. Look at this. This is also a DFA. From this state, there is a single transition on B, single transition on A. So a single transition on A, single transition on B. From this state, single transition on A, single transition on B. From this state, single transition on A, single transition on B. And for all input symbols for every state, the transition is defined. Right? So this is both an NFA and a DFA. Remember that every DFA is also an NFA. Right? We just discussed that a while ago, right? So very simple examples. Let's look at slightly different examples. If I want the length of my word to be exactly 3, okay, I want to accept those words or strings whose length equals to 3. We've seen these examples in DFA, just to remind you that. This is very simple. So this basically measures that my length equals to 0. Whatever input symbol I get, my length becomes 1. Whatever input symbol I get, I'm counting my length 2, then length 3. This is my length 3, right? Once I get length 3, I'm not defining any edge like this, because then it will become length 4, length 5. I want to accept exactly when the length equals to 3, right? So this will accept only if the length equals to 3. If the length equals to 4, see, you have reached here, there are no transitions defined on this, right? So this is actually an NFA, not a DFA, because we are not defining these transitions. What if I want the length to be less than equal to 3? That's very simple. You modify this slightly. The way you would do it is, on Q0, length 0 also should be accepted, right? Then length 1 also should be accepted. Length 2 also should be accepted. So this also becomes final state. Length 3 also should be accepted. Length 4 should not be accepted. So there is no loop here. What if I want length greater than equal to 3? Again, a subtle change. Okay. It's a small change on this. This is length equals to 3. Length greater than equal to 3. So this is length equals to 0 on any input, right? Length equals to 1. This state corresponds to length equals to 1. This state corresponds to length equals to 2. This state corresponds to length equals to 3. So equal to 3 is taken care of. If my length is more than 3 also, I should accept it. That's all is my finite automata. Okay. Now let's look at this. My length is 2 mod 3. Okay. Because I have mod 3, let me design 3 states. Q0, Q1, Q2. Corresponding to the remainder value of 0, 1 and 2. Because I want 2 mod 3, this will be my final state. Once I start here, look at this. If I get a character, any character or any input symbol, I go here. Any input symbol, I go here. Any input symbol, I go here. Now this is your DFA. This is not an NFA. This is a DFA. Or in other words, since every DFA is an NFA, this is both a DFA and an NFA, to be precise. So let's actually summarize some of the observations that we have had, right? So if you think about it from a computational standpoint or from a software standpoint, right? Or from a software standpoint, DFA is easier to implement. DFA is easier to implement, right? It's easier to implement and computationally more efficient, right? Is easier to implement and efficient. Efficient in what perspective? Efficient from a computational standpoint, because you don't have to track multiple paths, multiple transition paths, etc. So DFA is more efficient than NFA. That's one observation. Second observation here is, again, we'll show this. For every NFA, we can construct an equivalent DFA. Okay, we will show that in the next few videos, right? So for every NFA, there is an equivalent DFA, right? So the power or the capabilities of NFAs and the power or capabilities of DFAs are the same. Because for every DFA, you can construct the equivalent, for every NFA, you can construct the equivalent DFA, right? So if you look at languages that NFAs accept, for every language that an NFA accepts, you can find an equivalent DFA, which also accepts that language. You can, right? So having said that, the design of NFA is easier. Design of NFAs, as we have seen a bunch of examples, right? Design of NFAs is easier, especially in complex situations. Especially for complex cases, especially for complex systems or complex cases, right? So that's why people like them, because they're very easy to actually design to start with. And you can think of NFA as a parallel computing engine. You can think of NFA as a parallel computing engine, right? Because at any point there are multiple paths that I need to keep track of, right? Again, parallel computing, because, or you can also think about it as a multi-threaded system. Again, if you don't know what multi-threaded is, that's perfectly all right. We learn that in operating systems, right? That's another way of looking at it. Now, again, another very important thing is there is no need. So there is no need of dead states. There is no need of dead states, as we have seen in the case of in the case of NFS, right? So that's all. And remember, always remember, this is a key thing, that there are multiple transition paths possible. There are multiple transition paths. This is the most important property. There are multiple transition paths possible, and some transitions may not be defined. This is also important. Some transitions are not defined. Some transitions are not defined in the case of an NFS, right? That's a fundamental difference between NFS and DFS. Just wanted to collate or to list down all the observations that we've had by solving a bunch of problems.